Yeah, it'll be a bit bluish in the center.
Right. Eugene, do you want to explain what's going on? What have we done?
We have heated the copper sulfate powder.
What colour was it originally?
It was originally blue and it turned white after heating
Why did it turn white?
because it dehydrated after the evaporation of water.
Alright. Now, did that require a lot of energy or a small amount of energy?
A large amount of energy.
Yeah, alright. So that indicates it was probably an endothermic reaction going in the forward direction, so heading towards the dehydrated copper sulfate. And this is incredibly hot now, so we're going to let it cool down. And we're going to add that small amount of water there back to the copper sulfate, and we want to see whether that's going to be endothermic or exothermic. Alright, as we just saw, we're looking at a reaction between copper sulfate pentahydrate and watching it be dehydrated. So dehydration into copper sulfate plus water. So you might ask yourself, how is this a reaction or reversible reaction? How will it demonstrate a reaction? Well, let's actually look at what copper sulfate, and I'm going to do it in blue here, copper sulfate pentahydrate is, because I mean it looks odd with that little decimal place there. Essentially what it's saying is that within the copper sulfate crystal structure there's 5 waters. So what would that actually look like? Well, I'll give it a go of drawing it. I'm gonna stuff it up for sure, but I'll give it my best shot. So we know that copper is a transition metal. It's got electrons sitting up there in the d orbital, and in fact it can far exceed that octet rule which you're kind of used to from year 11, and it can have far more electrons than that in its outer shell. And what it can form is an octahedral arrangement of water ligands. Ligands are just components attached to a central metal atom, usually a transition metal in the middle. And so it has these waters attached. Oh, that's a very weird way of drawing that. There we go. And it says 3, 1 going down, then we've got the ones coming out the back, OH2, and then another one out the back here. Okay, and then coming up to make the octahedral arrangement is the sulfate. So coming out like this. So this is just one small component because it's actually a crystal structure. So this is, you know, infinitely large essentially. And what actually happens is this substance here is this substance, okay? So what happens is when we heat it, so when we apply a little bit of heat, as you can see here, heat, and we applied it with a Bunsen burner, what we do is we drive off, the heat drives off these water components, leaving us with just our copper sulfate and then water. So what will that actually look like? Well, the copper sulfate, so this blue copper sulfate up here, will actually turn white when it loses its water, and then we will actually start to collect a small amount of water. So that water there that was in the crystals, all these things are driven off, they move up here as a gas, down through the delivery tube and into the test tube down the bottom here. And what we've done in this test tube is we've added ice cubes. So here are my ice cubes. make it quite cold. So when that gaseous water hits the sides of the test tube, it condenses out and then collects down here at the bottom of the test tube. Okay, so then we're left with two components, our white copper sulfate up here, and so it's essentially pure copper sulfate now, and our water. So there's a few safety concerns in this little demonstration, or this practical, and that is that if we overheat copper sulfate, so once we drive off all the water and we continue to heat the copper sulfate, we might start producing sulfur dioxide gas, which isn't great. It will, it's quite toxic. It's one of the things that's responsible for acid rain, and you can think if you're breathing sulfur dioxide, it would then react with the water in your lungs to form, sulfuric acid, and then possibly even sulfuric acid. So not great for you. Don't breathe it in if you can avoid it. And that's what would happen if we heated this for too long. So once you see the whiteness, you want to stop, because beyond there, you'll start decomposing the copper sulfate into those dangerous gases. Now, the second safety concern, little skull and crossbones. That's a skull and crossbone. And then the second safety concern is once we've produced our water here, if we want to then show the reverse reaction, so the hydration, it doesn't really like what I'm doing here. The hydration of the copper sulfate back to the pentahydrate, then we want to add that small amount of water we took out, and we want to just add it back in. But if we add it back in straight away, we've heated our test tube significantly, so it's quite hot. And if we were then to add water into that, we'll then get all these little, well, not even little, we'll probably end up with these big cracks forming across our test tube, so it would crack off. So we don't want to do that. We're going to wait for our test tube to cool down first. Then, as we'll see in the next little clip, we'll add that back. Now, it required a lot of energy to go this direction. We had to apply a lot of heat to dehydrate this pentahydrate, and that indicates that it's probably an endothermic reaction going in the forward direction, so plus delta H going in the forward direction. And what that then would indicate going back in the hydration direction, it would be a negative delta H. So we learned that in year 11, and you learned that according to Hess's law, and it's also really important as we move through the equilibrium unit to understand that if something is endothermic one direction, the opposite direction must be exothermic, and vice versa. So knowing that, when we actually rehydrate our copper sulfate, hopefully what we see that turns back blue, and hopefully also if we just do it very qualitatively and touch the test tube and see whether it warms up when we do that. Okay, so let's actually take a look.
Right now.
Alright, hang on before we start. That is the water of crystallization, so that's the water that we've removed from that copper sulfate. That was an exothermic process. We're expecting to see an that was an endothermic process. Now we're expecting to see an exothermic process going this way. So the temperature
should rise of the copper sulfate.
Yeah, exactly. No worries, see you later. Alright, now give that a shake. Alright, what have we seen happen?
Turn blue again.
Turn blue, perfect. Alright, so we've got the copper pentahydrate.
It's warm.
Oh yeah, significantly warmer, isn't it? Yeah. Excellent.